After solving the centers of our 4x4, as well as pairing up our edges, we've reached the final stage of the reduction method, which is to effectively solve the cube as if it were a 3x3. However, there are a couple of interesting cases that we can run into, known as parity problems, and so I'm going to explain those in this video. So after solving the center pieces into their correct positions, as well as pairing up our edge pieces, we can go ahead and solve this 4x4 as if it were a 3x3 cube by pretending that these two pieces are one edge and these four center pieces are one center on a 3x3, and the corners remain the same as if they were a 3x3. So we can go ahead and solve our cross, for example, this piece here, move in this white and red one, a white and orange one down here, and lastly our white and green one. So that's how we do the cross, and then from there we'd go on and do our F to L and our last layer. However, in 75% of your solves, you'll run into what's known as a parity problem. So these situations arise when you're solving the 3x3 stage, but you run into a situation that isn't solvable using normal 3x3 techniques. The first example of this is when you get to orienting your last layer. So normally you'll have an even number of edges that you need to flip around the top layer. So you'll either have 0, 2, or 4 edges misoriented. However, on a 4x4, you can get what's known as OLL parity, which is where you have this edge pair essentially flipped in its place. And you actually have a situation where you need to swap these two edge pieces to flip the whole edge entirely. So these will either be cases where you have 3 edges oriented or just 1 edge oriented on your last layer. There's an algorithm that you can use to effectively flip this edge and get rid of this parity problem, which is known as OLL parity. And this algorithm is very long, very tedious, and it takes a little bit of time and practice to actually get used to it and memorize it. You'll get OLL parity every 1 in 2 solves, so there's a 50% chance that you'll get this problem. And when you do get it, the algorithm simply goes like this. So wide R, U2, X, wide R, U2, wide R, U2, wide R prime, U2, wide L, U2, wide R prime, U2, wide R, U2, wide R prime, U2, wide R prime, like that. The other parity problem that you can run into on a 4x4 is during the permutation of your last layer. So once you've oriented the entire last layer, if you're using full PLL, and if you know full PLL, then you'll be able to quickly recognize whether or not you actually have a valid PLL case. So in this example, solving as many pieces as we can, we actually have 2 swapped corners and we have a 3 cycle of edges. So this edge pair needs to go over here, this one to here, this one to here. So it's anti-clockwise cycle of 3 edges and a 2 corner swap, which is actually an odd number of piece swaps, which isn't possible on a 3x3 cube. If you're using full PLL, then you'll be able to quickly recognize whether or not you actually have a valid PLL case and execute the PLL parity algorithm that I'm going to show you shortly. However, I imagine most of you watching this tutorial are actually using 2 steps to permute your last layer. So by doing the corners first, and then by permuting the edges. So for example here, we can go ahead and permute our corners first, and then decide whether or not we have a PLL parity problem when we're permuting our edges. So here we can just use the algorithm which swaps 2 corners on the right hand side. So after we've permuted our corners, these 2 edge pairs are solved, but if we have a look around the back, these 2 edge pairs are swapped with one another. Now, because we're thinking about this like a 3x3, representing this state on a 3x3 cube is not possible because you can't have an odd number of piece swaps on a 3x3 cube. That is, you can't swap just one edge with another edge and not swap 2 other pieces around the cube. However, on a 4x4, this is possible because this isn't actually 2 pieces. We actually have 4 pieces here that we need to swap. So this edge needs to swap with this one, and this edge needs to swap with this one. So to deal with this problem and turn this into a state that's possible on a 3x3 so that we can go ahead and continue to solve it, the PLL parity algorithm that you can execute goes like this. So hold the cube from any angle and simply do small r2, so that's the inner r2, u2, small r2 again, u wide 2, so that's the entire top 2 layers, small r2 again, and then do a U wide 2, again like that. So after we've done that, we simply have a U permutation or a 3 cycle of edges. So we have this one needs to go here, this one needs to go here, and these 2 this edge pair needs to go over here. So we can solve that one with our normal edge cycle algorithm. So like with the OLL parity case, you'll run into PLL parity in 50% of your solves as well. So there's a 25% chance of running into both parities in one solve, and there's a 25% chance of running into neither parity in one solve. Thankfully, those are the only two parities that you can encounter, and so once you've dealt with those, then you should be able to solve your entire cube. So congratulations. In the following videos in this module, I'm going to go through an example solve, as well as give you some extra tips and tricks for solving the 4x4.